Okay, everybody, here's a video that I wanted to post about the atmosphere and the gases that make up our atmosphere and the layers of the atmosphere. And we'll get to that in a couple of minutes. One of the things that I wanted to do first was show you the barometer here and how it's changed since yesterday. A little bit of glare coming off of the lights on the ceiling there. We can see that. The little bit of glare right here, that's from the ceiling lights. But here's the barometer. I haven't touched it. It's a day later, and we could see where the brass needle on the barometer was, and the black needle shows us how the air pressure has changed. Not a lot of movement, but a little. And we can see that the air pressure went up a few millibar from where it was before. As the air pressure increases, that means an improvement in the weather. It's getting better. And we can certainly see that. I know that you can't see out the window, but it's a very sunny day here. Clear blue skies. Barely a cloud in the sky. So as the air pressure increases, the weather gets better. Now, to keep track of this, and we did this in one of the other videos, I'm going to take my fingers and move this brass dial, and I'm going to turn it and put it on top of the black needle. And again, the black is the one that moves with the changes in air pressure. The brass one is the one that I move, and it basically just serves as a placeholder. So I know what the air pressure was, and then I can see how it's changing. Air pressure by itself is only so useful. Really, you want to know how the air pressure is changing. Is it increasing or is it decreasing? What's the trend? We would say barometric trend. Barometric pressure is a term for air pressure. So what's the trend? Is it increasing or is it decreasing? Well, it's been pretty steady, but it has increased a little bit, and that means good weather. So we'll keep an eye on this and see what happens next time. So I'm going to set this aside, and the next time we do a video, we'll take another look and see how it's changed. Okay, so I'm going to put that aside. Now, let's start taking a look at the atmosphere, because that's really what this is all about. So we can really define the atmosphere as the mixture of gases that surround Earth. Everybody knows that. Started the right sound. That surround Earth. But something that's important to think about is we have this mixture of gases around our planet. And that's actually a special thing, even though we don't really think about it much. The moon has really no atmosphere. And I think we talked about this once at the very beginning of the school year. The moon is just small, and for that reason doesn't have much gravity. And since it has little gravity, it doesn't have the ability to really hold on to gases. They basically just drift away into space. The Earth is a large enough planet to have enough gravity to hold on to its gases and have a real atmosphere. Other planets have atmospheres, very different composition than ours. What's always kind of funny to look at is old science fiction movies, and people like in Star Trek and similar shows are walking around without spacesuits and space helmets on and just breathing the air on other planets. But the odds of another planet having the same atmosphere as ours is very, very low. So anyway, let's take a look at our atmosphere. The majority of our atmosphere is made up of nitrogen. Nitrogen gas. When we take a breath and we breathe in, we're breathing in mostly nitrogen. Close to 80% of the gas that we breathe in is nitrogen. And plants use this nitrogen and convert it into cellular tissue and so on, and make proteins and so on, and it's what they use to grow. About 21% of the atmosphere is made up of oxygen. So a common misunderstanding with our atmosphere is it's mostly nitrogen. A lot of people, even adults, think that the air is mostly oxygen, but it's actually mostly nitrogen and then oxygen. And then we have, if we think about the percentages and we add these up, well, we don't have much left. We have 1%. And that 1% remainder is all of the other gases that you can think of. And you could probably think of some other gases. Gases like, for example, argon make up 0.84%. Argon is a noble gas on the periodic table, all the way to the right, non-reactive. Argon is used by welders and for other industrial purposes. We have carbon dioxide, CO2, at only 0.03%. And this is, of course, the gas critical to photosynthesis. Then we have all other gases. And you've certainly heard of some, like, for example, helium. We can find helium in the atmosphere, but in very, very small percentages. Hydrogen, again, very small percentages, but it's there. Ozone, probably heard of ozone. And other gases too, things like neon, and xenon, even krypton, noble gas on the periodic table. All of these gases combined make up a very, very small percent of the atmosphere. But we can harvest these gases with special factories and extract them and concentrate them and use them for industrial purposes, filling helium balloons, and all kinds of other things. And then we also have other things in the atmosphere too. We have things like water vapor. Water in the form of a gas. H2O in a gas state. Water vapor. We also have dust particles. Dust particles would include everything from, well, little bits of soil to pollen, volcanic ash, and all kinds of other little bits of things, even pollutants, little bits of soot from burning coal and things like that. So that's what makes up our atmosphere. Now, if we take a look at the layers of the atmosphere, well, we have this atmosphere, but we could arrange it essentially by density. Near the surface, we have mostly nitrogen and oxygen. Oxygen gas that we breathe in is actually O2. An oxygen and an oxygen bonded together. Then higher in the atmosphere, we would have just pure oxygen. Helium, higher up. Hydrogen, even higher. So we have these gases in layers. We have this separation of the gases. The atmosphere is not uniform in its composition from the surface to space. We have this separation of gases. Let's just skip over these things for now. Now let's take a look at this graph. We can see temperature here, and here we have Fahrenheit. Maybe we'll work in Fahrenheit because that's the temperature scale you're almost certainly most familiar with. So we have 0 degrees Fahrenheit going all the way up to 120 or so. And then here we have 80, 40, 0, and then we're in the negatives. Well, you've probably learned since you were very young that as you get higher in altitude, like climbing the top of a mountain or flying high in an airplane, that it gets colder as you go up. And that's true, but only kind of partially true. It's true in the lower levels of the atmosphere. On the y-axis or vertical axis, we have altitude in miles. Well, near the surface, at an altitude of 0, that's true. And close to surface, that's true. So as we go up a tall mountain or maybe up in an airplane, the temperature is going to get colder as we go up. I'm going to grab a ruler to draw a line. So I'm going to connect these 2 points. And these 2 points show that as we increase in altitude, it gets colder. And that's what you've learned before. It's colder high above. But if we keep going up in altitude, like with a big balloon, like a hot air balloon, or maybe a rocket even, and measure the temperature, this is higher than airplanes fly. It's higher than any mountaintop. We actually see something very strange. And the temperature profile reverses. And what this means is that when we're near the surface, it does get colder as we go aloft or above. But once we reach this point, then the temperature changes, and we have an increase with altitude. It actually gets hotter. And then if we keep going up in altitude and measuring the temperature between these points, we see it getting colder again. like we would expect. And then we end up with this very kind of odd zigzag pattern to the temperature profile of the atmosphere. So as we go up in altitude, it's not as simple as just saying it gets colder. That's really true in the lower levels of the atmosphere. But as we get higher and higher, it gets more complex. And we see this increase in temperature. Then we see a rapid decrease in temperature. Right, colder, just keep it consistent. Then it gets warmer as we go towards the edge of space. And if you were to launch a rocket into space, you have to go through all of these different temperature extremes. Now, this is kind of odd. Why does it get colder as we go up? Well, that in itself is kind of an interesting thing. You've always been told, well, it gets colder on top of a mountain. Well, it's just simply there's less air. And with less air, we have fewer particle collisions. When the molecules are not colliding, we have less friction, we have less heat, we have colder temperatures. This part of the atmosphere is called the troposphere. And this is where we live. It's where airplanes fly and our mountaintops are. The next layer of the atmosphere, where the temperature increases, is called the stratosphere. The stratosphere is up above the mountains. It's up above the altitude of most airplanes. Most aircraft would not fly in the stratosphere. Birds, of course, don't fly in the stratosphere. It's above most weather. Our weather systems, like storms, are down here in the troposphere, not in the stratosphere. And we have this increase in temperature. And it turns out that we have this increase in temperature because this is where we have the ozone layer. And those gases, the ozone gas, traps light. It traps UV energy, ultraviolet light, which is invisible to us. But that added energy causes an increase in temperature that we see in this part of the profile. Once we get above the ozone layer, we no longer have that heat-trapping ozone gas, and temperatures get cold again. And then we get into the thermosphere, and this is where particles from space get trapped, and we call this the thermosphere. We have an increase in energy here as well, and we see higher temperatures. And I know that explanation was a little vague, but that's okay. So in between the troposphere and stratosphere, we have what's called the tropopause. It's just the boundary between them. And then here we have the stratopause. Over here, this is called the mesosphere. Meso basically means middle. It's middle of the atmosphere. And this would be the mesopause. The boundary between each layer of the atmosphere is defined by a pause. Now, just to conclude this video on the layers of the atmosphere, on your reference table on page 14, you have this graph. You have this profile. So if you're ever asked about it, here's temperature in degrees Celsius. They did it in Celsius, but it's the same idea. And we can see it getting colder, warmer, colder, and hotter in the thermosphere. Here are the altitudes and so on. So sometimes you'll be asked about this. It also shows you air pressure, and that we could see that the pressure goes down with altitude, and even water vapor. And a minute ago I mentioned that most of the weather is confined to the troposphere, and this is really why. In order to have clouds and rain and storms, you need water. And almost all of the water vapor is in the troposphere and not in the stratosphere. The stratosphere is just simply too dry to drive our weather systems. And so that was just a quick little overview of temperature and layers of the atmosphere and the gases that make it up. Okay, so that's all for now, and the next video will be about what's called insolation. And we'll talk about that in a few minutes.